Discovering the electron. By the end of the 19th century, many physicists were comfortable that nearly everything had been discovered and explained. There was Newtonian mechanics, Maxwell's equations, which unified electricity and magnetism, thermodynamics, which said that heat is another form of energy, the speed of light was measured, no stationary reference frame was found, which helped lead to Einstein's special theory of relativity in 1905. But then things started popping up, like the electron. About 150 years ago, cathode rays were discovered. No one knew what they were. Physicists working on the problem just knew what they could see. What they saw was that when a high voltage was applied between two metal plates inside an evacuated glass tube, a shadow was cast on the glass behind the positive plate, and the glass surrounding the shadow glowed. The glow was enhanced when the glass was treated with fluorescent chemicals. This effect implied that something was traveling in a straight line from the negative plate towards the positive plate. The positive plate stopped some of it, creating a shadow surrounded by the glow. Since the rays seemed to come from the cathode, they were called cathode rays. Light casts a shadow, so it could be light, or it could be a stream of invisible particles. Without opening the tube, what are two ways you could check to see if the rays were charged particles? One idea is to apply an electric field across the path of the rays. If they are charged particles, they'll be deflected. If they're electromagnetic waves, they will not be. The direction they are deflected would also indicate whether they are negatively or positively charged. As shown below, positively charged particles would be deflected downwards by this external electric field, while negatively charged particles would be deflected upwards. Another idea is to apply a magnetic field, shown here with red X's, across the path of the rays. If they are charged particles, they will be deflected. If they're electromagnetic waves, they will not be. The direction they are deflected indicates whether they are negatively or positively charged. Using the right-hand rule, positively charged particles would be deflected upwards by this magnetic field, while negatively charged particles would be deflected downwards. As it turns out, both electric and magnetic fields deflected the rays, consistent with cathode rays being negatively charged particles. Also, it was found that changing materials for the cathode had no effect on the results. In 1897, J.J. Thomson used this experimental procedure of using magnetic and electric fields to learn more about these particles. He and his assistants adjusted the fields so they pushed the particles in opposite directions and canceled out, resulting in the particles going straight through. Here's a replica of the Crookes tube used by J.J. Thomson at Cambridge University. Electrons were emitted from the cathode on the left and were deflected by an electric field set up in the middle of the apparatus. The velocity of the particles was found by measuring the magnitudes of the electric and magnetic fields and using Newton's second law. Since the electric field and the magnetic field were set and measured, the velocity could be found. Right? If you did a free body diagram for one particle, and if it's going straight through, you know that the force up must equal the force down because there's no upwards or downwards acceleration. So therefore, the force up minus the force down equals 0 because acceleration is 0. Plug in the equations for magnetic force and electric force, and you see that the velocity must be the magnitude of the electric field divided by the magnitude of the magnetic field. If they turned off the electric field and there was only a magnetic field, the particles would be deflected downwards, as shown below. By observing where the particles struck the tube, causing it to fluoresce, they were able to measure the radius of the semicircular path. This enabled them to determine the ratio of the particle's charge to its mass, Q over m. To find the charge to mass ratio, use the following. Newton's second law, the particles having a velocity of e over b, which we already determined, And the magnetic field provides the centripetal force that moves the particles along the semicircular path. So because they're moving along a circular path, the acceleration is centripetal, so we can replace A with v squared over r. The magnetic force is qvb on a moving charge. And then we can rearrange this to solve for q over m. So we're going to move this m over to the left side, and we're going to move this vb over to the right side. Now one of these v's is going to cancel, right, leaving us with just one velocity on top. B is moving to the bottom, m is moving to the left side. And we already figured out that velocity must be e over b, so we're replacing v with e over b, so we end up with b squared instead of just b. And the charge to mass ratio was determined, 1.76 times 10 to the 11th coulombs per kilogram. Thomson found that this particle had a very low mass for its charge. In fact, its mass per charge was 1,800 times less than the previous lowest amount measured for a particle. Before this work, physicists were speculating that the hydrogen atom was the smallest fundamental particle. This led Thomson to propose that this negatively charged particle was new, and he called them corpuscles. The name electron was taken from George Johnstone Stoney's work in 1874 and proposed again by George F. Fitzgerald, and the name stuck. Furthermore, since the electron was so much lighter than the hydrogen atom, it was concluded that it must be part of an atom.